Our next step in our education about partition functions is now to apply the partition function that we've derived for translation and first of all derive the system translational partition function and then use that to calculate the average energy. So that's going to be the game plan for this particular video. So I'll remind you that the result we got for the translational partition function for a molecule looks something like this. It's equal to 2 pi m kBt over h squared, and we raise that to the 3/2 power multiplied by the volume. Now, for a variety of reasons, I'm going to probably want to express this in terms of beta, so I'm going to undo something I did in the previous video and write this as 2 pi m over beta h squared raised to the 3/2 power times volume. All right, it's the same thing. Now, we also have learned that the system partition function for any system can be written as the molecular partition function raised to the number of particles divided by that number factorial. So now if I use that here, I'm going to find that the system translational partition function would look something like this, where I'm going to have 2 pi m over beta h squared, and now it's raised to the 3/2 power raised to the n, so it's going to be to the 3n over 2 power. So it's a very high power. And the volume will be raised to the nth power. All right, so this is how a system translational partition function might look under these circumstances. Now, when we talk about the average energy for this system, okay, this is one where we will want to calculate from our formula, and I'll remind you what that formula is, the following derivative. We will want to take the derivative with respect to beta of log of this partition function over here. And so now this is why I wanted to express this function in terms of beta instead of in terms of kt. Now, we're taking the derivative of this logarithm, and I want to use some properties of logarithms to actually make taking this derivative a little bit simpler. All right, so if I write out what this logarithm looks like, so let's just put this over here to the side. The logarithm of z cis is going to be the logarithm of this big mess, 1 over n factorial times 2 pi m over beta h squared raised to the 3n over 2 power times volume to the n. Now, I know if I have the logarithm of a product of two numbers, that's just equal to the sum of the individual logarithms. So I'm going to use that in this case to separate out all these various pieces. I also know that the logarithm of a ratio is going to be the difference of the two logarithms. So that can take care of this part with that. So now this logarithm of z translational, the system translational, can be written out as several log terms. So I'll have log of 2 pi m over beta h squared raised to the 3n over 2 power plus log of volume raised to the n power minus log of this number n factorial. Now for this one and this one, I can also use a property of logs that says that if I have log of x to the a, that's just equal to a times log of x. So I can bring the exponent down in front, and I can do that here with this exponent and with this exponent. So I'll have, this is equal to 3n over 2 times the log of 2 pi m over beta h squared plus n log v minus log of n factorial. And I'm going to make one further simplification, and notice that this is a log, and notice that I have beta here in the numerator. What if I write this thing as log of 2 pi m over h squared minus log of beta? All right, well, I can do that, but I have to pay attention to the fact that both of them have this prefactor. So in fact, I can extend that logarithm by writing it like this. It's equal to 3n over 2 log of 2 pi m over h squared minus 3n over 2 log of beta plus n log v minus log of n factorial. Okay, so I've done a lot of work on this logarithm, and you may be wondering, why would I do that? Well, this is why I would do that. I'm taking a derivative up here with respect to beta. Now, when I look at all of these terms down here that come from that log of z system, this has no dependence on beta, this has no dependence on beta, and this has no dependence on beta. So when I take the derivative with respect to beta of these terms, it's going to be 0. The only term that contributes to a derivative with respect to beta is this term here. So now, and I've got a minus sign there, so I was going to cancel the minus sign here, so this is going to be equal to the derivative with respect to beta of 3n over 2 log of beta. Okay, we've just made our problem a whole lot simpler. This doesn't depend on beta, so I can bring it outside the derivative, and I'll end up with 3n over 2, the derivative with respect to beta of log of beta, and that derivative is just 1 over beta. So I'll end up with the result 3n over 2 beta, or 3/2 n kbt. And I hope you recognize this result. It's one that we got early on in the very first lesson when we talked about the ideal gas and the average kinetic energy. That's exactly what this is. It's the average kinetic energy for a gas in a box.